Welcome to Worksheet 2, Quantitative Energy Problems Part 1. For each of the problems, we're going to sketch a warming or cooling curve, in other words, a temperature time graph, to help us decide which equations to use to solve the problem, and then we're going to round correct sig figs. I want you to write 3 sig figs. Okay? 3 sig figs. Now, what do I mean about which equation or equations to use? Well, anytime that there's a temperature change, you're going to be using Q equals MC delta T. Anytime there's a phase change, you're going to use Q equals the mass, M, times the heat of fusion or the heat of vaporization, so these two equations. And to remind you that this is freezing and melting, and the heat of vaporization is vaporizing or condensing or boiling, evaporating. Those are the phase changes that we're dealing with here. Q is always going to be our heat energy. M is the mass. C is going to be our heat capacity. And delta T is always going to be the final temperature minus the initial temperature. And this is all going to be degrees Celsius. Don't do Kelvin. Now, for water, our heat of freezing and melting is going to be 334 joules for every gram, and our heat of vaporization is going to be 2,260 joules for every gram. For temperature changes, if we're dealing with a solid, the heat capacity is 2.1 joules for every gram Celsius. And the heat capacity for liquid water is going to be 4.18 joules for every gram Celsius. And we are going to deal mostly with water. If we're not dealing with water, the problem will give you this information for whatever substance you're looking for. When we're solving these problems, our strategy is going to be 1, sketch a temperature versus time graph, a heating curve. You're going to determine how many parts there are to the graph, and assign equations to each. Okay? We're going to list what word problem gives us, plus what we know from equation bank. And we're going to substitute and solve for unknown. So this is our basic strategy. You're going to start with your heating curve, determine how many parts there are to the graph, and assign equations. Then list what the word problem gives us and what we know from the equation bank. And we're going to substitute this information into our equations and then solve for the unknown. So what does this look like in practice. So let's solve this first one together. We have a cup of coffee at 140 degrees, or 140 grams, and it cools from 75 to 20 degrees Celsius. And we want to know energy, okay? So I see and hear that I have a cup of coffee, which is gonna be largely water, and it cools from 75 to 20. And since 75 and 20 have nothing to do with 100 degrees and 0, I know I'm not gonna get a phase change because we're not near the boiling point or freezing point of water. So on my curve, I'm gonna do 75 degrees Celsius, 25 degrees Celsius, and I'm gonna start at 75 and end at 25, right? So that's step one. Now I need to determine how many parts there are to the graph. Well, I have a downward part, but that's it. I don't have any flat parts. I don't have any more downward or upward parts. So I have one equation. Okay, which equation is it gonna be? Well, we just talked about how our temperature is nowhere near freezing, melting, vaporizing, or condensing point of water, which is 0 degrees or 100 degrees. So the only equation I'm dealing with is Q equals mc delta T. I'm gonna write that up here, or right here. Q equals mc delta T. Right, did 1, did 2, now I'm gonna do 3. List what word problem gives us and what we know from the equation bank. Okay, so word problem gives us a mass of 140 from 70. That means that our initial temperature is gonna be 75 degrees Celsius. And we're gonna go to 20 degrees Celsius. We want to know Q. And looking at this, I have my mass, I have the information for the change in temperature, I need to know Q. That means that I'm missing the C. Well, where do I get C's? I'm gonna get it here in my equation bank. I have two options here. I need to ask myself, am I dealing with solid water or liquid water? A cup of coffee at room temperature is gonna be liquid, so I'm going to list this 4.18 on my thing too. So C of liquid is gonna be 4.18 joules per grams degrees Celsius. Cool. Before I go, I do have to calculate delta T. So delta T is going to be T final minus T initial. It's really important that you do put this in the right order because you need the negative sign. So my final temperature is 20 degrees Celsius. My starting temperature is 75 degrees Celsius, and that gives me a change of negative 55 degrees Celsius. That negative is really important. I'll explain in a moment. All right. Now we're on to step 4, substitute and solve for the unknown. Okay, so my equation is Q equals mc delta T. So I get Q equals M times C times negative 55 degrees Celsius. Fantastic. I see that I have, if you look at units, I have joules over grams degrees Celsius times grams. My grams cancel out. of joules over degrees Celsius times a Celsius. My Celsius cancels out and we're left with joules, which is fantastic because energy is measured in joules. That's what I want. So I'm going to put this into my calculator. Let me open my calculator. My big giant calculator. And I get 140 times 4.18 times negative 55. Oop, that it didn't leave the negative in there. That's okay. Since I know that there was a negative in there, this is going to be negative 32,186 joules. And I said above that I want 3 sig figs. This is my 3rd sig fig place. So it ends up being negative 32,200 joules. The reason why this negative is important, because negative means, or negative Q means lose energy. A positive Q means gains energy. And we can see it is lost energy. So the correct answer has to have a negative. Otherwise, you're saying we put energy in. Okay? Okay, let's take our next one. Here's our strategy. We have our equation bank up here. So let's go through this. We're going to read through this. The first step is to sketch our graph and determine our equations, list what we know, and then substitute and solve. Okay. During volleyball practice, you lost 910 grams of water due to sweating. If all this water evaporated, how much energy did the water absorb from your body? Well, first things that I notice here is I'm given a mass, but I'm not given the actual temperature change or like any temperature numbers. This is a big clue for me that what we're dealing with is a phase change. So anytime you don't have a temperature change, you're here. Now, the other clue that this gives me is the word evaporated. So we know evaporation involves going from a liquid to a gas, so that just supports the fact that I'm dealing with a phase change. Now, I happen to know the temperature that water changes from a liquid to a gas is 100. So I'm just going to draw a flat line at 100 because there's no temperature change going on. We're just evaporating. So that's step 1. Now I need to use this flat graph all the way up here as a determination of which equation to use. Now, as I said before, there's no temperature change, so I know that we're using this equation, or that we're not using this equation, that we're using instead one of these. So I need to choose the right one. Are we dealing with freezing and melting, going from a solid to a liquid or a liquid to a solid, or vaporizing, condensing, going from a liquid to a gas or a gas to a liquid? Well, evaporation is the process of going from liquid sweat to gaseous water. So I'm going to use this equation. Okay, now I'm going to list what I know. Well, I know the mass is 910. So I've got the mass. I want to know Q. That means that I need to fill in HV, which is nice because, look, it's given to you right here in the equation box. So I'm going to put HV equals 2260 grams per joule, or joules per gram. Great. Now all I have to do is substitute and solve. Q equals 910 grams times 2260 joules per gram. Now, before I continue on here, I need to consider one thing. Remember how I said that a negative Q means energy is coming out, we're losing energy, and a positive Q is energy going in? I need to pause here before I do my calculation and ask myself, am I losing energy or I'm gaining energy? Well, here I have a liquid turning into a gas. I'm going from really tightly connected, doing this, to really far apart. And so in order to do that, I have to put energy in to pull things apart. That means that I should indeed have a positive energy change. So I'm going to put that positive there to remind myself this should be positive. Okay, now that I've done that, I'm going to come to my calculator. I'm going to put in 910 times 2260. And it's a big number. That makes sense. I'm making almost a kilogram of water into a gas, and each gram is 2,000. That makes a lot of sense. So I have Q equals 2056600, and since up here I have joules or grams and grams over or joules over grams, what I'm left with is joules, and I want to make this 3 sig figs. My third spot is right here. What's next door is a 6. So I'm going to write this out as Q equals 2060 joules. Okay, there's problems 1 and 2. Hit up my next video for 3 and 5.